In this session, we will discuss about nyquist stability criterion. First of all, let us see the mathematical preliminaries for nyquist stability criterion. Suppose there is a function f of s and it is a function of s, and we can represent this f of s as the ratio of two polynomials. That means f of s can be written as s minus z1 into s minus z2 etc. up to s minus zm divided by s minus p1, s minus p2 etc. up to s minus pn. And here z1, z2, z etc. up to zm represents the zeros of the function f of s. p1, p2, p3 etc. up to pn represents the poles of f of s. See, if we are plotting this s, that means s comprises of two parts, that is real part and imaginary part. Suppose we can write s as sigma plus j omega. Then sigma comes in the x direction and j omega comes in the y direction. So any point in the s plane, that means sigma plus j omega represents the s plane. Any point in the s plane can be converted to a function f of s. So when we are substituting the point in the s plane in this function f of s, we will get a value for f of s. That means a point in the s plane can be converted into a point in the f of s plane. See, since s is a complex variable, the function f of s will also be a complex quantity. So for any value of s, f of s also have some value, and we can represent that value of f of s as u plus jv, where u is the real part of f of s and v is the imaginary part of f of s. So we can say, we can define another complex plane called f of s plane with coordinates u and v. See, s is a complex plane with coordinates sigma and j omega. Similarly, a function of s which is f of s we can use as f of s plane and its coordinates are u and v. So for a particular value of s, there will be some value for f of s. So for a particular value of s, the f of s will represent a point in f of s plane. So now we are dealing with two planes, s plane and f of s plane. For a particular value of s in the s plane will correspond to f of s value in the f of s plane. So we can say that therefore for every point in s in the s plane at which f of s is analytic, there exists a corresponding point f of s in the f of s plane. So we can say that the function f of s maps the points in the s plane into the f of s plane. So also, a function is said to be analytic in the s plane provided the function and all its derivative exist. The points in the s plane where the function and derivative does not exist are called singular points. So f of s should be, if we can say that f of s is a analytic function only when its derivative and that function f of s and derivative of that function exists at that point. If its derivative does not exist, then that point is called a singular point. And suppose we are taking two planes, s plane and f of s plane, and we can represent the contour of in the s plane or graph or in the s plane like this, and then there should be some f of s contour in the f of s plane. Actually this is not the correct one. Actually for showing the relationship between s plane and f of s plane, we are simply taking this contour. So this is an arbitrary contour in the s plane and its corresponding contour in the f of s plane is like this. See, there will be some arrow mark. And next, there is a concept encircled and enclosed, and we will see what is encircled and enclosed. You can see different figures, figure 1, figure 2 and figure 3. And in this figure 1, you can see that there is a circle, right? And it is in the aromatic indicates that it moves in the clockwise direction. So there is point A inside this contour and also there is a point B outside this contour. So a point is said to be encircled by a closed path if it is found inside the path, and here you can see that A is enclosed within the A is within the path which is shown here. So this point A is said to be encircled in the clockwise direction. That means point A is encircled in the clockwise direction. See, this is the clockwise direction contour or curve, or it is a closed path. So the point A will be encircled by this closed path. And here we can say that point B is not encircled because it is outside this closed path. Similarly, next is enclosed. Any point or region is said to be enclosed by a closed path if it is found to lie to the right of the path when the path is traversed in the prescribed direction. See, here there are two figures, figure 1 and figure 2. The shaded regions in the figure 2 and figure 3 are regions which are enclosed by the closed path. See, this is a closed path and this shaded region indicates the region which are enclosed by this closed path. Similarly, here the shaded region is outside, and this indicates the path. This shaded region indicates the regions which are enclosed by this closed path. So with reference to the figure 2, the point A is enclosed by a closed path and point B is not enclosed. In the figure, point A is enclosed by this closed path because it comes in the shaded region, and here point B is not enclosed because it doesn't comes in the shaded region. Similarly, in the figure 3, the point A is not enclosed by the closed path because A situated in the is situated in the non-shaded portion, so it is not enclosed by this closed path, but B is enclosed by this closed path because it is situated in the shaded portion. So this is the concept, encircled and enclosed, and this concept will be useful when we are drawing the nyquist plot. Okay. So here are some examples of f of s and f of s plane contour and s plane contour. See, left side represents the s plane contour because you know that in the case of s plane contour, x-axis is sigma and y-axis is j omega. Similarly, in the case of f of s plane contour, there is x-axis is along u and y-axis along jv, and so a curve or contour or closed path in the s plane is mapped to this f of s plane like this. See, suppose f of s is equal to s square minus 2s plus 6. We can partition, or we can make into factors as s minus 1 minus 2j and s minus 1 plus 2j. So s value will be equal to 1 plus 2j and 1 minus 2j. So 1 plus 2j corresponding to this point. See, this term is the numerator term, so it represents the zeros. So zeros will be represented by the circles. So Z1 and Z2 are the zeros. There are no poles for this function. So we marked Z1 and Z2, and you can see that in the S plane, the S plane contour is encircling the Z1 and Z2. You can see here that it encircles in the clockwise direction. So zeros Z1 equal to 1 plus 2j and zeros Z2 equal to 1 minus 2j. And this contour in the S plane correspond to this contour, this type of contour in the f of s plane. You can see that here these zeros are located in the right half of the s plane. When the zeros are located in the right half of the s plane, then the similar contour in the f of s plane should be rotating the origin 2 times, and that too in the clockwise direction. So if the s plane closed contour encloses said number of zeros in the right half of the s plane, then the corresponding contour in the f of s plane will encircle the origin of f of s plane set times in the clockwise direction. See, here you can see that there are 2 zeros in the right half of the s plane, and this contour, s plane contour, encloses 2 number of zeros, 2 zeros. So in the f of s plane, the f of s plane contour will encircle. If it encloses 2 zeros, then this f of s plane contour encircles the origin 2 times in the clockwise direction. That is shown here. This is the clockwise direction, and this is also clockwise direction. Here the origin is encircled by this f of s plane contour 2 times. So that is the point. And here for the development of the nyquist criteria, the exact shape of the contour is not required, but only the number of encirclements of the origin of the f of s plane is essential. That is why we are dealing with the encirclement of the origin. And next we will consider another function f of s is equal to 1 by s square minus 4s plus 8. And in this case, when we are factorizing it, we will get two different points. You can see that here the values of s represents the poles. So s have values 2 plus 2j and 2 minus 2j. When we are plotting, you see these are the poles, so we can mark it as a crosses, and two poles are marked as p1 and p2. That is along 2 plus 2j and 2 minus 2j. And you can see that S-plane contour encloses these poles, and similar corresponding to this S-plane contour, the f of S-plane contour is shown here, and you can see that it is encircling the origin of the f of S plane 2 times, right? So we can conclude that if the S plane closed contour encloses p number of poles in the right half of the S plane, then the corresponding contour in the f of S plane will encircle the origin of the f of S plane p times anti-clockwise direction. So you can see here that there are two poles, and so these two poles are enclosed within this S plane contour. So corresponding f of S plane contour will encircles the origin 2 times. That is the point here, and that too in the anti-clockwise direction. If the function has zeros only, and that zeros are enclosed lies in the right half of the S plane, and they are enclosed by the S plane contour, then the corresponding f of S plane contour will be encircling the origin in the clockwise direction 2 times. So next you can see that the function is f of s is equal to s minus 1 into divided by s minus 2 into s minus 4. Here there are zeros and poles. Zeros are locating at 1 and poles are locating at 2 and 4. We can mark the zeros as circles and poles as p1, p2 like this. That is marked by crosses. And you can see that S plane contour encloses these zeros and poles. So, and the corresponding f of S plane contour will be like this. That will encircle the origin. That is f of S plane contour will encircle the origin a single time. See, here the number of poles is represented by p and number of zeros is represented by z, and here p is greater than z. Then in such cases the contours in the f of S plane will encircle the origin of the f of S plane p minus z times in the anti-clockwise direction. Here it is encircling the origin in the anti-clockwise direction. Also here p minus z means the number of poles minus number of zeros, so that is equal to 2 minus 1, that will be equal to 1. So this f of S plane contour will encircle the origin a single time, and that too in the anti-clockwise direction. So in the case of poles, the encircling will be in the anti-clockwise direction, and in the case of zeros, encircling will be in the clockwise direction. Here next case we will consider that f of s is equal to s square minus 2s plus 6 divided by s minus 2. In this case also we will factorize the numerator, and we will get 2 zeros and 1 pole. Pole is locating at 2 and zeros will locate at s is equal to 1 plus 2j and s is equal to 1 minus 2j. So in this case you can see that this there are poles and zeros, and these poles are marked as crosses like this, and zeros are marked as circles, and there are 2 zeros and 1 pole that is lying on the right half of the S plane. And you can see that S plane contour encloses these 3, and the corresponding f of S plane contour, you can see that it is encircling the origin in the clockwise direction. So from this we can see that if the S plane closed contour encloses z zeros and p poles in the right half of the S plane, and if p less than z, then the corresponding contour in the f of S plane will encircle the origin of f of S plane z minus p times in the clockwise direction. See, here the number of zeros is higher. So number of zeros is 2, number of poles is 1. That is 2 minus 1 equal to 1. 1 encirclement will be in the f of S plane. And see, here the number of zeros is higher, so the encirclement will be in the clockwise direction. And next we will consider another case. See, the f of s will be in the form s square minus 2s plus 6 divided by s square minus 4s plus 6, 4s plus 8. In that case, you can see when we are factorizing, we will get different poles and different zeros. And see, poles are marked by cross marks, and zeros are marked by circles, and you can see that S-plane contour rotates or encloses these zeros and poles in the clockwise direction, and so corresponding f of s plane contour will be in the clockwise direction, but it will not encircle any origin. That means if an S-plane close to contour encloses z zeros and p poles in the right half of the S-plane, and if p equal to z, then the corresponding contour in the f of s plane will not encircle the origin of f of s plane. See here, number of zeros is equal to 2, number of poles is equal to 2, therefore their difference will be equal to 0. In such cases, there will not be any encirclement of the origin by the f of s plane. Similarly, we will consider the next case, f of s is equal to s minus 2 into s minus 1 into s minus 3. In that case, the poles will be marked as P1 and P2, and that is locating on the real axis, and zeros will be locating on the real axis itself, and that these three quantities will be lying in the right half of the S-plane, and the corresponding f of S-plane contour is shown here, and it moves in the clockwise direction, and you can see that there is no encirclement of the origin by this f of s plane. So if the s plane close to contour does not enclose any pole or zero, then the corresponding contour in the f of s plane will not encircle the origin of f of s plane. So this is a mathematical prerequisite, and so we can say that if n is the number of encirclement of the origin and z is the number of zeros and p is the number of poles, then if n is positive, that means n is positive means we will take the difference between z and p. N is positive, then the direction of encirclement of the origin f of s plane will be anti-clockwise direction. So n positive means n is equal to p minus z we will take, and if n is positive means that means the direction of the encirclement of the origin of f of s plane will be anti-clockwise, and if n is equal to 0, then that means that z is equal to p, and in such cases there will be no encirclement of the origin of f of s plane. And in third case is if n is negative, the direction of the encirclement of the origin of f of s plane will be clockwise. So that's all about this topic. Thank you.